Hello, my name is Frank Walpole and I head the technical support department at Concurrent Technologies. As you know, Concurrent Technologies manufacture and design single board computers based on Intel processor. So we've got SBCs of different form factor. We've got VME, Compact PCI, AMC and VPX. But today I would like to tell you more about something that we've been doing for quite a few years now, which is VPX system development. And I want to tell you more why we felt that it will be a very good idea for our customers to provide this as a service, how to design a VPX development system. I'll start by explaining the difference when it comes to system design using some of the legacy technology or systems that our customers have been using. So starting with VME, building a system with VME was very easy because you could plug any board in any slot and it will just work. You didn't need to worry about, okay, what slot? Okay, you need to make sure that the I/O at the rear transition module is matching where you plug the board, but that's all you needed to worry about. Another example of legacy technology, still going strong though, including VME, is Compact PCI. With Compact PCI, there was one thing that you needed to know, and it was very easy to remember because one of the slots was marked in red, which is the slot where you plug your system controller, which initialized your peripheral card, but that's all you needed to remember. You could plug any peripheral card pretty much in any slot, and it will just work. Now, these two legacy technology, when it comes to the data bus and address bus, this will go to all the slots, and that's why it was very easy for them to use any board in any slot. The technology moved on, and to increase the bandwidth between slots, this has all been serialized. So you end up with something called serial fabric, where you have point-to-point communication. And this has also been used in backplane type technology. So an example is micro TCA. So although micro TCA is point-to-point, it still is fairly easy to use because everything has been frozen and defined such that all the slots connect to a central switch called the MCH. And there is very limited I/O also defined with micro TCA. Micro TCA.4 for the physics community, there you have the addition of an RTM, a rear transition module, micro RTM, so you can also have I/O at the rear, whereas with micro TCA pretty much all the I/O were at the front. But like I said, the I/O were all predefined, which make it a limitation, but mean that it's very easy to use. Now, VME is widely used still, but the problem is you needed something to move forward with new technology. So serial fabric with VME started with VXS, but now needed to move on to help with the swap. So this is where Vita46 was defined for VPX, which defined the connector, where the signals are, and also Vita48 to help with the ruggedness of VPX. The problem with these, especially Vita46 on its own, it was too wide open, so something was required to help system designer. And this is where Vita65 or OpenVPX was created, where with OpenVPX you have backplane profile defined, so it makes it easier to use the technology because there's a number of backplane that exist, and also help with interoperability a little bit. Moving on, this carries on, the work that was done with OpenVPX carries on in the US with an initiative called SOSA, where the idea is to pretty much almost do the same as what was done in micro TCA, where all the signals on the pin have been predefined. So the idea is that it will then help interoperability. You will be able to use in a given slot board from different manufacturers. That will help the ecosystem, hopefully potentially reduce the price of VPX product. But it's a compromise. So if everything is predefined, you have limitations. So some of the things you can do with OpenVPX, as now, where you have lots of I/O, will not be possible in the same manner with SOSA product. But right now, because many customers are pretty much new to VPX and using OpenVPX, I want to tell you more about why you have to have a different mindset when it comes to using VPX. And I'll use 4 different types of backplane, all 6 slots, to illustrate the point where you need to worry about how the backplane is wired. You can't just plug a board, a VPX board, in a chassis without this information. So the first example is similar to the compact PCI system I mentioned earlier, where you have one payload slot in slot 1 that control and initialize a number of peripheral slots. You can see here that the connection between slot 1 and slot 2 is thicker than the other one. It's because it's a fat byte, a by 4, whereas to the other slots, it's a by 1. So if you have a GPGPU and you want efficient bandwidth between the processor card, for example, and your GPGPU, it has to be in slot 2. It may work in the other slots, but here you have a limited bandwidth because it's just a by 1 versus a by 4. And you also need to make sure that the board you're using in slot 1 can support this 1 by 4 plus 4 by 1 for it to see all the peripheral slots. If you don't have a board that supports this 1 by 4 plus 4 by 1, you can use tricks. So for example here, the board, the payload slot, the payload card only supports 2 by 4, but it can still see and control more than 2 peripheral by using a specific card that will have a switch and fan out to additional peripheral slots. So this is an example on how to control more peripheral card, even if your payload slot only support 2 by 4. A more elegant solution is to do what, for example, MicroTCA is doing, where all the board goes with a fat pipe, a by 4, to a central switch. So you can then have lots of peripheral cards in here controlled by one board. You just need to tell the switch where is the system controller. If you, for example, want to use Ethernet to communicate with the board, it still is possible to have communication, for example, via PCI Express, and you do that using what is called an expansion plane. But you then need to make sure, if this has been wired, that when you plug a board, the expansion plane, and especially the connection, the hardware connection between expansion plane, won't cause any damage to your board. So this is where you have to know how the backplane is wired. If you cannot find any profile for your application, especially during development, you can do this communication yourself. So you will then need to use what is called a power and ground backplane, where there is no connection on the backplane or power and utility. There's minimal connection, and you make the connection yourself using what is called Maritime cable. Now, you may say that, yeah, how do I start? Well, to make it easy to start, Concurrent Technologies have decided to, make available to customers different type of chassis for development. So these are chassis where, if you want to start, you can use a small, basically a chassis where you only have one board, or use, for example, the system which I talked about, where you use a switch if you already know you want to start with a number of boards. If you want to do something more radical, from the start, you know you have to build a demonstrator, you know the type of board you want to use, but you don't have the knowledge or the time to investigate the intricacy of the PINA, the intricacy of the VPX specification, and this is where we can help, because this is the sort of thing that we are doing on a daily basis, where we basically advise customers around the world on how to build a VPX system. So there's a few things you need to know to make sure that you don't make any costly mistake. So these are examples of systems that we have provided to customers. So some of them could be development system, all conduction cooled, so it's very easy then to translate that to something that is deployable. If, for example, there are budget limitation or restriction, we can go halfway and design a system with boards that are air-cooled, but we'll ensure that all the connections at the are at the rear, so that it's very easy to transfer that to all conduction-cooled board. Or if, for example, you have to provide a number of these development systems to various software teams, we can have this design as a air-cooled system with I/O at the front and I/O at the rear via RTM. So all this is possible. So like I said, we've been doing that for a number of years now. So here's our example of system we've put together. So these are the last three we're going to have to ship to a customer. These are to be used by a software development team. Their requirement here was that they needed a lot of core. So we've decided to use our Xeon processor board. That allows them to have very efficient communication between the boards using 10 gigabit Ethernet via our switch. They also needed, for example, an accelerator card with a CUDA, so working with some partners that we've got, we've validated a GPGPU. They also had the need to access various sensors via Ethernet, so we've got additional Ethernet card to connect all the sensors. So we validated all this. We've installed CUDA on the system, making sure that everything works. We've also validated VMware because this is how they wanted to make use of all the core. So once they receive the system, all they'll need to do is to plug it in, install their software, and there you go, that's it. They don't need to worry about the intricacy of VPX. We took care of all this for them, and we provide all the documentation required. So if you have any similar need and you don't know where to start, please do not hesitate to contact our sales team. We'll be more than happy to help you there. Thank you.